Okay, moving on to example 2, which is production of chlorine using the diaphragm cell. So once again, you're given a diagram and you're given some extra piece of information. Let's just start by looking at the diagram. I have very kindly labeled the cathode and anode for you. It also doesn't show the power supply, but it is an electrolytic cell. Just take my word for it, I guess. Concentrated sodium chloride solution is coming in. So this is seawater, and there is a diaphragm, and there are a few arrows for output. So a few things we produce here. So extra pieces of information: the electrodes are inert, and the electrolyte is a saturated solution of brine. So this sodium chloride in water. However, the concentration is definitely not SLC. It's definitely not 1.0 mole. I'm pretty sure seawater is like way more concentrated than that. So the type of cell here, for looking at inert electrodes, still aqueous electrolytes, water is still present, but the condition is non-SLC. So this is going to be the first example when we look at non-SLC condition, and the actual non-SLC part here is that you have high concentration. So the concentration of sodium chloride, remember the square brackets are used to denote concentration, is much, much greater than 1.0 molar. Okay. So let's start with the first question. What is the purpose of the cell? Once again, you can see this in the title. The purpose of the cell is to produce chlorine gas. And once again, I'm going to point out that chlorine is a diatomic element. So it exists as Cl2 and not Cl by itself. So please don't just write Cl. That makes no sense. So you want to essentially get chlorine gas from this cell. Chlorine gas is really useful. They started using chlorine gas as a weapon in World War I, and this is Fritz Haber, who was one of the first person who suggested the use of chemicals in as a weapon. Anyway, he was a brilliant chemist and an interesting character. We'll come back to him later. But they still produce a lot of chlorine these days, so you can make PVC and other things. What is this? Oh, are we talking about purifying water? Yes, I think so. Oh, there's paper. Okay. So a very, very useful product, even though hopefully we no longer use it for chemical warfare. Anyway, let's start with the next question. How does the cell operate? So I'm going to start with the cathode, the anode, and the electrolyte. So I think the anode and cathode are already identified here. The anode panics, so positive anode, and negative cathode. And the electrolyte, this is the electrolyte. Well, this is the only solution that's left. I don't think this diaphragm is an electrolyte. So this is the electrolyte. Okay, write the half equations. Oh, what's happening? Let's talk about the half equation. So you have, if this is your electrolyte, then essentially the species that you have present would be Na. So you have concentrated NaCl. So you have NaCl AQ, which means that you have Na plus, Cl minus, and H2O. So you have 3 species present. So if I use the electrochemical series, do I only talk about this side? Oh yeah, because the concentrated sodium chloride solution only goes from this side. So let's just start with this side first. The diaphragm does allow water and ions to go through. So some solution is going to go to this side, but I kind of need to work out what reaction is happening at the anode before I can consider the cathode. So let's start with the anode. So there are 2 things present. So you have Cl minus and H2O. Na plus is not a reducing agent. If you look at the electrochemical series, this is somewhere on this side, so it's not going to participate in this particular competition anyway. So if you look at the electrochemical series, then water, do I write anything? No. If you look at this electrochemical series, water is the stronger reducing agent, so water would react. Let's just write that. So H2O is the stronger reducing agent. Which means that H2O would react, would be reduced. Sorry, oxidized. So H2O would be oxidized, and it's going to give you oxygen. hydrogen ions and electrons. However, that is a problem because I kind of don't want oxygen to be produced at all, because the whole point of this cell is to produce chlorine gas. So if water is oxidized instead of chloride ions, and how do I get my chlorine gas? That's the issue. So the reason why that is an issue is because this is actually not the reaction that's going to take place in this particular cell. And that is because the condition is not SLC. So this prediction that I made would only apply if you use the electrochemical series and assume a concentration of 1.0 molar. So if you have a concentration of 1.0 molar of Cl minus ion, then yes, maybe water is going to be a stronger reducing agent, because the strength of the reducing agents is only determined by the value of the E naught here. So this one is a little bit smaller, so it is a little bit stronger. And that would only work if the concentration of chloride ions is 1.0 molar. However, in this particular context of this cell, which is the diaphragm cell, the concentration of chloride ions is not 1.0 because, as I mentioned earlier, the condition is non-SLC. So in that case, using the electrochemical series is not going to work out too well. That's just what I just said, so you can read this later if you want. So the electrochemical series cannot accurately predict the strengths of oxidizing or reducing agents under non-SLC conditions. So these numbers are not actually that valid because the condition here and the concentration here is so much bigger. Well, the concentration of chloride ions anyway. And so what happened here is, and this does not work all the time, okay? You cannot say, oh, something is just very, very concentrated, that's enough, it's going to react instead. This is a very, very specific case, and probably the only case that you have to remember. But chloride ions in water have very, very similar E naught values. So let's start with that. So one is 1.36 and the other is 1.23, and I'm just going to highlight these two, which are the stuff that we're talking about. First of all, they already have very, very similar E naught values. So the difference in strength of reducing agents is not that big. It's not like this one is 0.36 or 0.23 or anything. So it's already very, very close to each other in terms of strength. And water is only slightly stronger. So when the concentration of chloride ions is very high, which in this case is seawater, chloride ions would react preferentially at the anode, producing chlorine gas. This is the only case you have to remember when a substance having a higher concentration, allowing it to be able to compete with something that in the electrochemical series is supposed to be the stronger reducing agent. So the reaction that you actually get, do I write the equation? No. The reaction that you actually get is going to be 2Cl minus going to Cl2 gas and 2 electrons. So this only works because the solution that you're using in this particular cell uses a very high concentration of chloride ions. So this is just a summary of the three cases. The effect of concentration of chloride ions on the products of electrolysis of sodium chloride. So this is just what I just said again. So the case that we have here is this one, when the concentration of chloride ions is very high. So you're not going to get chlorine gas being produced if you use a diluted solution of sodium chloride. But if you use a highly, highly concentrated solution of sodium chloride, chlorine gas could potentially be a product that you get. And then somewhere that is high, but like not really high, maybe diluted seawater, but not diluted, so the concentration is still higher than 1, for example, then you can potentially have both of them being oxidized, and you're going to get a mixture of oxygen gas and chlorine gas at the anode. So this happens as well, but when that happens, the question will tell you that more than one gas is produced, and then you can make a prediction. Unfortunately, I cannot give you a definitive range of concentrations that will tell you, okay, so if it's in this concentration, you get chlorine gas, in this concentration, and you get water and chloride ions, because it also depends on the temperature and other things. So you really need to pay attention to the question to know whether you get one gas or two gas and which gas. So in this case, I know I cannot just have oxygen. I cannot have oxygen because it's production of chlorine. You know, if you do chemistry in university, we will tell you exactly how to determine the products of electrolysis and considering concentration when you calculate E values. This is just the theoretical, and then there's the actual E value. So you should do chem at uni, is what I'm trying to say. I scared my brother off. He's not doing chemistry at uni. So sad. All right, so we're going to write the half equations at the anode. So at the anode, I'm going to get, yes, let's do that. So we have Cl minus going to Cl2 gas, and what am I doing? 2 electrons. So let's think about what comes in. So you have Na plus, Cl minus, and water coming in. Okay, so the Cl minus turns into Cl2. I think that's what comes out here. That looks like an A. Cl2 gas. Cations go to cathode, so Na plus is going to cross the diaphragm to go here, and I think some water is going to go here as well. Okay, so your cathode, you might potentially even have some unreacted chloride ions, because I think it's probably not feasible to assume that every single, because again it's a highly concentrated solution of sodium chloride, so it is likely that some of the unreacted chloride ions, some chloride ions would cross the diaphragm and go to the cathode before it can actually react with the anode. So your cathode is going to have sodium ions. Well, the solution at the cathode has sodium ions, water, and maybe some chloride ions as well. So that is the flow of ions. I think I need to actually talk about what happens at the cathode now. So you have Na plus, water, and Cl minus. Cl minus is here, it's not going to do anything. Do I do this? Yes, I did. Okay. So you have Cl minus, water. So that's the anode. But the cathode, you have water and Na plus. So at the cathode, water is a stronger oxidizing agent by a lot. It's not a small difference. And then you might wonder, well, does that mean because Na plus is very concentrated that sodium ions is going to reduce? No, it will not reduce. Water will reduce because the difference is really big. I think all right. The way you want to remember is the only time when something can outcompete because of high concentration is this pair. This is the only pair you need to memorize for VCE. So just don't impose that knowledge to other things. So water will react at the cathode. So we're going to have 2H2O plus 2 electrons going to H2 gas and 2 OH minus. So the OH minus is going to be here. I don't think it's going to come back. It doesn't have to. But I guess it can. But yeah, it's not going to come back because the positive ions already go forward. You probably don't need both. And then you have hydrogen gas coming out here. So this product that you're collecting, it's going to be a solution of sodium hydroxide, basically. So NaOH, AQ, which is caustic soda, which is also a very useful byproduct. This is a very good cell. It has hydrogen gas as a byproduct, it has this as a byproduct, and it has chlorine gas as a primary product. There may be some like contamination with chloride ions in this solution. I don't think you can avoid that, but still it's a fairly good byproduct. And an updated version of this cell actually solves this problem and has a better device to make sure that the chloride ions can't go through. So describe the collection of materials. Again, chlorine gas and hydrogen gas are separated from each other. And this is why the diaphragm is here, because it prevents chlorine gas from being able to go to this side. So it just can go up and then it gets collected separately. So Cl2 gas and H2 gas are collected separately. Okay. All right, so this is an animation of how this works. Let's just go through this again. I'm gonna play this. I didn't want to show this earlier because it's a little bit terrifying. Let's start with this. Does this thing have noises? Wow. So you start with the saturated bright. Let's start with the input here. Let's start here. So saturated seawater solution coming in, and then you can see, I think I'm going to play it again. You can see that the chloride ions get oxidized to chlorine gas, so the chlorine gas will go out, and then the bribe will passes through the diaphragm, so there is sodium ion going through. Let's see whether these chloride ions will come through. Oh no, what? Okay, well, some of the chloride ions does come through, if you can see here. And on this side, water is being reduced because there's hydroxide ions coming out of this, which is the cathode, and then there's hydrogen gas coming out. There is no way I could do this animation. I got this from a website. And then you get your product, your byproduct, which is hydrogen gas, and then you have caustic soda with some contaminated chloride ions as well. And then they say there's diluted here. Oh, yeah, because the concentration is decreased over time. That's it. That's the diaphragm cell. Last question, what is the function of each component of the cell? Electrodes to provide side transfer as well. The electrolyte, so they can ask you, why do I need to use concentrated sodium chloride? So the high concentration of chloride ions is here so that chloride ions can preferentially be oxidized at the anode. This is the word that we really like to use in this situation when you explain, is preferentially oxidized. So I'm not saying that chloride ions is a stronger reducing agent. I'm saying that because of the high concentration, it is now preferentially oxidized at the anode over water so that chlorine gas is produced. The other feature that they can ask, and I can just simply ask, what is the function of the diaphragm? What will happen if the diaphragm is not there? The diaphragm is to prevent movement of gases. So if you go back to the animation, you can tell the chlorine gas comes out on this side and the hydrogen gas comes out on the other side. Okay, so diaphragm is to prevent movement of gases so that the hydrogen gas and the chlorine gases cannot come into contact with each other and react spontaneously. So that's good, because chlorine and hydrogen, once again, two products of electrolysis, could react spontaneously with each other. That is a bad thing. You also want to prevent direct contact between chlorine gas and hydroxide ion, which is the other product of reduction in this case, because if they come into contact, again, spontaneous reaction, not good. Hydrogen, once again, is highly flammable. Chlorine is toxic, if you don't know. Is that considered common knowledge? You should know this. So you kind of don't want an exothermic reaction between these two gases. That is just a recipe for disaster. So you also want to allow for safe collection of these gases, the toxic one and the flammable one. So that's it for example 2. Oh, just in case you're wondering what the diaphragm looks like, I found this. I think they don't really use diaphragm anymore. There's like a membrane now, because one of the original diaphragm that was built for this cell has asbestos in it, which was not supposed to use anymore. It's like a solid. It looks like that. That's the material. I don't know how thick the diaphragm actually is. And this is an example of what the cell looks like. Everything is sealed for good reasons, but I think you can have different valves, so the different gases that are produced can come out, I suppose. Anyway, so it's still like there's a lot of chlorine being produced these days still. Okay, so actually no, that's it. This is example 3. We're done.